my favorite problem of the whole year because I get to draw a banana. It's ridiculous, but you know, I have all the colors on here, so why not? So remember, we're now doing angled launch projectiles. Up till now, the projectiles that we have been doing, and did anybody do any problems, any physics problems over break? You should have, to keep your brain fresh. Okay, good. Doing those horizontal launch problems keeps your brain in it. Over Christmas break, I always have a prescription for doing like 20 minutes of physics a day. Take Christmas off, take New Year's Day off, or New Year's Eve, pick one. Like pick 2 days over break to take off, but other than that, do a physics problem every day over break, just to keep your brain fresh. All right, these are, up to now, all the objects that we've been looking at have had no initial y velocity, which makes a whole lot of things really easy. It makes half of our equations on the y-axis disappear. Poof, puff of smoke, they're gone, easy to handle. Now, we got things that have both x and y initial velocity. So we are looking at objects that travel up like this. Most of the same problem-solving techniques that we used in the horizontal launch still hold true. We're still going to list variables on the x and y axis. That makes things much, much easier. That was actually a real breakthrough for me because I struggled with these problems when I started teaching physics, and I would have to do these problems like 3 times before I walked into class so that I knew I could consistently do the problem. They're tough. Doing the separate axis listing really helped me, and I think it will help you too. So we are told that a zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, the zookeeper kneels 10 meters from the light pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. The monkey tries to trick the zookeeper by dropping a banana, and then continues to hold on to the light pole. At the moment the monkey releases the banana, the zookeeper shoots. If the tranquilizer dart travels at 50 meters per second, that's its initial velocity, will the dart hit the monkey, the banana, or neither? Whoa. All we're really interested in is the trajectory of the dart. That's it. That's really what that question is asking. So I'm going to start off, as always, by drawing the picture. What we're really interested in, I'm going to make the little tranquilizer dart a red spot there. What we're interested in is where on the y-axis, that's our question mark, this dart is when it gets to 10 meters on the x-axis. Because remember, we said, I told you this a million years ago when we were last here together, that this crazy revolutionary thing, for every moment in time there is an x and a y position. And we can use time as the bridge to tie the 2 axes together to figure out the position and motion of an object at any single point in its trajectory. That's pretty cool. So, they're asking, does it hit the monkey? Well, what are we really saying? Well, we're saying, where is it on the y-axis when it gets to 10? So let's start listing variables. Okay, we're starting off with initial velocity. That's where we usually start. So we got VIX, we got VIY. This is a trick question. I'm warning you in advance. Were you given VIX or VIY? Nope. What were you given? You can open your book and go to the problem if you want. You were given VI. If you are given a vector quantity such as VI, do you know some way to break that down into its component vectors? Why, yes you do. You're good at this. This is easy. You can do this in your sleep. So if this is VI, and that is theta, what would VIY be? VIY would equal VI times sine theta. Yes? What would VIX equal? Here's VIX, the adjacent side to the angle. It'd be VI cosine theta. So I'm going to list my variables in my table just like that. VI cosine theta, VI sine theta. And there are a number of reasons for not putting actual quantities in there yet. Leaving them as expressions is really far superior because it allows us to do what I like to call algebraic magic a little later. So I'm going to get rid of my, well, let's see, pause. Just as a bit of an aside, it's not totally an aside, can we find theta? Do we have the capability of finding theta? Because we kind of need that, don't we? We do. Well, we know that the distance between the tip of the gun and the light pole is 10 meters. The tip of the gun is 1 meter off the ground, and the light pole is 5. So what do we have here? We have 4 meters. Can we find theta with that? How? Do we know the hypotenuse? Inverse tangent. So if we do inverse tangent of opposite over adjacent, 4 over 10, that'll give us, whoops, not 0, theta, dummy. Okay, we're going to tuck that knowledge away. So when we get to that point, we know how to find theta, and that's a good thing. Let's go back to listing some variables here. What else do we know? So we've got VIX and VIY. We have expressions written for them at any rate. Do we know A sub x? Is there any acceleration on the x-axis? Nope. There is no rocket pack strapped. This is not a missile. This is a dart. Is there any acceleration on the y-axis? Yes. And that would be negative g, which would be negative 9.81 meters per second squared. Do we have a displacement on the x that we're interested in? Are we interested in any particular point on the x-axis for this object's path of travel? Yeah. Do we want to know do we want to know about this thing at 2 meters out, or 3 meters out, or 5 meters out, or 12 meters out? No. We want to know where this thing is on the y-axis when it's 10 meters out on the x-axis. What about displacement on the y-axis? That's our question. That's what we want to know. Where is this thing on the y-axis when it hits 10 meters on the x-axis? Now, as we've done in every other case, guess what time is? You can all say it together. The bridge! The bridge! Okay. I might have to make you stand up and play London Bridge with time or something. I don't know. Something to get the blood flowing. They had to pet imaginary cats in chemistry, so don't mess with me. Oh yeah, they did. Launched projectiles. Same equations we used with horizontal launches, though we have some differences. Obviously, VIX's are no longer going to cancel out, but A sub x's still are. So what if we create an expression on the x-axis from what we have? And I'm probably at this point going to delete this, get rid of this, and move a few things around here. Do you have an equation that will tie together VIA, delta x, and delta t? Yes, delta x equals VIX delta t plus 1/2 a sub x delta t squared. Now, it is super, super, super important to make sure you have those subscripts in there. Because we're going to start taking, and we started this already, but it gets more intense here. We're going to be taking an expression for things that are happening on the x-axis or the y-axis, and an expression that connects those events. And we have to make sure that we're only tying together those events. We can't cross axes yet. Until we do a substitution, we cannot have information from both axes in the same equation, not until we substitute. Okay, so is there anything here that goes away? Yep. That cancels everything out because a sub x is 0, so it sort of vaporizes the entire second half of the equation. We can solve this for delta t, and we get delta x over VIX. Now, if you want to, and I actually do think that this makes it easier on yourself. If you look up here, you'll note that VIX is VI cosine theta. I find it really handy at this point to go ahead and make that first substitution, delta x over VI cosine theta. So we have an expression for delta t. Good. Now, Do we have an expression on the y-axis that would tie all the variables that we have there together? Yeah, same darn one. Delta y equals VIY delta t plus 1/2 a delta t squared, and that's a sub y. And this is actually what we're going to solve from. This is what we're going to proceed from. So I'm going to cut that. I'm going to go ahead and pull this up to here. And because that delta t is the same on both axes, I can take this expression that I created for time using information from the x-axis, and I can substitute it into those two locations. This is just what we've been doing. It's just a little bit more complicated now because we don't get half of the second equation to go away. So the algebra is a little bit funkier. So we're going to go delta y equals, well, VIY is actually equal to VI sine theta. Hey, what do you know? Cut. So I'm going to do that substitution. And delta t is actually equal to delta x over VI cosine theta. All right, so far so good. And now I'm going to need a little bit of room because this is 1/2 a sub y. I'm just going to copy this whole thing. Can I manage it? Perhaps, perhaps not. Paste. Squared. At this point, I have everything that I need to solve this equation. And the nice thing is, because I'm solving for delta y here, I don't even need to do any rearrangement. I just have to simplify to a point where I can start plugging stuff in. So, delta y equals, well, I'm going to go ahead and multiply. I'm going to distribute the VI sine theta across the parentheses. So I now get, whoops, VI sine theta delta x over VI cosine theta. So I already have one nice little thing that's going to happen. I'm going to distribute the 1/2 a sub y across the parentheses. I should note, we have to square everything in the parentheses and nothing that was outside the parentheses. Do you want me to show that step, or is it okay to move forward? Do you want me to show every step? Because I'll do that on the first one. Let me show every single step. So before I even distribute the a sub y, I've got delta x squared over, and this is important, VI squared cosine squared theta. We write cosine squared theta because we're not squaring theta, we're squaring the cosine of theta. And we'll talk about how to enter that on your calculator to not screw up your numbers and have a calculator error on your test. Okay, so now that I've got that, I can go ahead and distribute that 1/2 a sub y. Delta y equals, oh, well, hey, look at that. VI cancels. That's nice. I like that. I love it when things cancel. So now I have sine theta delta x over cosine theta plus, and I'm going to go ahead and distribute. So I have a sub y delta x squared over 2 VI squared cosine squared theta. Can I do anything else to this equation? There's one other thing I can do to this equation to make it a little bit simpler, but it's not entirely obvious. Have you guys done any trig identities yet? Do you know what sine divided by cosine is for any angle? Tangent. Yes, it is tangent. And we'll walk through the proof of that in a little bit. But for now, you could stop simplifying here, plug all your numbers in, and go. You could do that. But especially when we get into the bigger, hairier algebra, and it does get hairier than this, it's helpful to know that sine divided by cosine equals tangent because it allows you to trim things down a little bit, and that's good. It's one less thing you're calculating that you can make a mistake on. So I'm going to go ahead and do the shortcut. We'll prove it later. So we have tan theta delta x plus a sub y delta x squared over 2 vi squared cosine squared theta. Okay, we're ready to plug in numbers. Oh wait, did we ever find theta? We didn't. So we do have to go back and attend to that one little piece of business. That's this. Inverse tan, you all have your calculators out, right? Inverse tan of 4 over 10 equals theta. Do not round that number when you get it. Okay, so I've got 21.801, on and on and on and on. It's continuing, equals theta. So I'm going to do my normal sort of notation here. Tangent of 21.8, etc., times 10.0 meters. And I'll move this over so that I have sufficient space, plus negative 9.81 meters per second squared times 10 meters squared over 2 times 50 meters per second squared times cosine squared of 21.8, etc. Okay. Substantial opportunities for calculator error. Be careful, kids. The TI-30s or TI-30 multi-views. If you do cosine of, 21.801, etc., 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 and then hit enter, you get the number that is the cosine. If you then hit squared and enter, you get the cosine squared of that angle. The other way to do it, so okay, so the first way, the sort of slow, clunky way, hit your cosine button, your number, which you should be able to pull down from up top, hit enter, you'll get another number, hit x to the square, x to the second, hit enter, and you're going to get your final answer. The other way to enter this, and I just did this successfully, so I do know it can be done, this will get you the same number. So start a parentheses, cosine, it will start a parentheses for your number, make sure you close those parentheses, then put in your second parentheses, then square that quantity, then hit enter, and it will get you the same number. But this is a great way to screw up on a test. Be really careful with calculator entry on these. I've done it myself. And actually the first time I ran all my numbers, I got like 4,000 and some, which I know is the wrong answer. It's not even close to reasonable. And I had to go back and re-enter everything. So be careful with calculator entry because you've got a whole lot of algebra behind it. And you want to make sure that if you've got all your algebra well done, you don't fall on your face with the calculator. So, okay, what do we get for delta y? Do you have a raw answer now? I have to go back up and find mine. What do you get? TI calculators will all give you a starting parentheses after you put in a trig function. If you don't close the parentheses after the angle number and you put in times anything, it's going to multiply the angle by that number, not the tangent of the angle by that number. So, calculator entry. Break this down. You should be getting 4.00000001 there. For the second half of that, the denominator should be 4,310.39. 369. It goes on and on and on. The numerator should be negative 981. When you go ahead and divide out the fraction, what you end up with for a delta y is 3.77240, blah, blah, blah. Okay? How many have you got there? Okay. The algebra is hard on these. The calculator entry is hard. You will get better at calculator entry with long problems doing these. So, what are we actually saying? Okay, we did a whole bunch of math. What the heck are we actually saying? Here's what we're saying. Here's the light pole. Here's the tip of the gun. Where is the dart 10 meters out? So it's here, 1 meter off the ground. It is 3.77 meters above where it started. So the dart is 4.77 blah 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 meters above the ground. it's important to note that your delta y here is not really your answer. You have to think about what the problem's asking. So the dart at 10 meters out ends up 4.77 meters above the ground. Where's the monkey? 5 meters above the ground. As long as the monkey is tucking its little butt and holding on to that light for all it's worth, this is an even worse monkey. The monkey should be fine. But that's not all that there was to the problem. Where's the banana? So, to solve for the position of the banana, does the banana have any x-axis motion whatsoever? Nope. Simple free fall problem. So this is really easy. We said that at the moment that the zookeeper fired the gun, the monkey dropped the banana. So what do we need to know? Well, we need to know at t equals what the bullet is at the 10 meter mark. And then we look at t equals whatever that is, how far has the banana fallen? We're actually not going to do that half of the problem. That's a more unusual application, and I want you to get the basics of the projectile motion first. So assigned are all the practice problems on page 104. Page 104, 1 through 5. You got today to work. We'll check in on these today. Tomorrow I will not be here. I'll be on a field trip with the biology students to the Carnegie Museum of Natural History. So you'll have time to work, and I will have the worksheet packets ready for you so that if you finish all the book problems and you want to move on to the worksheet problems, you can do that. Okay? That's it.